Hello everyone, we have previously learned about geometric sequence. Let's first consider a question. What is a geometric sequence? And what is the general formula for a geometric sequence? Generally, if the ratio of each term to its preceding term in a sequence, starting from the second term, is equal to the same constant, we call such a sequence a geometric sequence. It can be expressed as n divided by n-1 equals the common ratio q, where the common ratio is not 0. The general formula for a geometric sequence can be expressed as n equals a 1 multiplied by q raised to the power of n-1, where both the initial term a 1 and the common ratio q are not equal to 0. Let's move on to question 2. Have you all heard of chess? Have you ever seen a chessboard? Chess originated in ancient India. According to legend, the king wanted to reward the inventor of chess and asked him what he wanted. The inventor said, "Please place 1 grain of wheat on the first square of the board. On the second square, place 2 grains of wheat. On the third square, place 4 grains of wheat," and so on. The number of grains of wheat placed in each square is twice the number of grains in the previous square, until the 64th square. "Please give me enough grains of wheat to fulfill the above requirement." The king felt that his request was not too demanding, so he readily agreed. Please help the king calculate how many grains of wheat he should give to the inventor in total. Yes, he should add 1 to 2, then add the square of 2, the cube of 2, and so on up to the 63rd power of 2. So, how do we calculate this formula? Let's analyze it together. If we consider the number of grains placed in each compartment as a sequence, we can obtain a geometric sequence. It has a total of 64 terms, with the first term being 1 and the common ratio being 2. We are seeking the sum of the number of grains placed from the first grid to the 64th grid, which is equivalent to finding the sum of the first 64 terms of this geometric sequence. Calculating this expression without the aid of a calculator would take a considerable amount of time. Thus, we naturally wonder if there is a summation formula for geometric sequences that can assist us in solving this problem. How can we find the sum of the first n terms of a geometric sequence? In our previous study, we learned that there is a summation formula for arithmetic sequences. So, can you derive the sum of the first n terms of a geometric sequence by analogy with the method for finding the sum of the first n terms of an arithmetic sequence? Let's first review together the derivation process of the formula for the sum of the first n terms of an arithmetic sequence. The sum of the first n terms of an arithmetic sequence a 1, a 2, a 3, a n is Sn. According to the definition of an arithmetic sequence, the difference between the n plus 1 term and the nth term is equal to the common difference d. We derived the formula for the sum of the first n terms of an arithmetic sequence using the method of summing in reverse order. First, we combined all the terms. Then, by reversing the order of the sequence, we obtained formula 1 and formula 2. Adding the two equations, we get that 2 times Sn equals n times a 1 plus a n. Therefore, Sn equals n times a 1 plus a n divided by 2. Thus, we can use the nth term a n and the first term a 1 of an arithmetic sequence to represent the sum of the first n terms. Essentially, we are based on the definition of an arithmetic sequence, where a n plus 1 minus a n equals d. We use the property that the corresponding sums of the upper and lower terms in the two equations after reversing the order are both a 1 plus a n to construct identical terms. By eliminating the differences between terms, we simplify the complexity and derive the formula. So for geometric sequence, can we also use the method of summing in reverse order? Can we express the sum of the first n terms of a geometric sequence using its first term and nth term? Let's give it a try. First, add up all the terms, then reverse the order. However, in a geometric sequence, a 1 plus a n does not equal a 2 plus a n minus 1. Therefore, we cannot obtain 2 times sen equal to n times a 1 plus a n. After trying, we found that it doesn't work. So we know that the formula for the sum of the first n terms of a geometric sequence cannot be derived using the method of reverse order addition. Let's reflect on what we just tried. When summing a geometric sequence, we cannot simply copy the method of reverse order addition. Instead, we need to explore the essence of this method and the fundamental purpose of summation. What is the fundamental purpose of our pursuit of harmony? How to construct identical terms in the first n terms of a geometric sequence and eliminate the differences between terms, as well as remove the intermediate terms. Thus, simplifying complex problems is the key to solving them. In the case of an arithmetic sequence, we start by considering the common difference d. Therefore, in the context of a geometric sequence, we naturally wonder if we can utilize the common ratio q to help us eliminate the intermediate terms. We have made some improvements. To better understand the characteristics of the formula, we may express each term using the common ratio q and the first term, resulting in sen equal to a 1 plus a 1q plus a 1q square, and so on until a 1 multiplied by the n-1 power of q. Let's observe the characteristics of two adjacent terms in this formula. How can we transform a certain term into its subsequent term? Indeed, according to the definition of a geometric sequence, a n divided by a n-1 equals q. If we slightly modify this equation, we will find that a n is equal to a n-1 multiplied by q. That is, in a geometric sequence, each term multiplied by the common ratio q equals its subsequent term. Therefore, by analogy with the method of summing an arithmetic sequence, we need to construct another equation. To achieve the goal of eliminating the intermediate term, we need to ensure that the two equations have the maximum number of identical terms. So how can we construct this formula so that after subtracting it from the original formula, the middle term can be eliminated? Observing this formula, we need to eliminate these intermediate terms. To do so, we need to construct a formula like this: a 1 multiplied by q plus a 1 multiplied by q squared plus a 1 multiplied by q to the n to power. It can be obtained by multiplying each term of the original formula by the common ratio q. Therefore, we multiply both sides of the first formula by the common ratio q simultaneously, thus creating identical terms and obtaining the second formula. Then, we subtract the two formulas to get the result. Let's derive it in detail. Assuming the first term of the geometric sequence a n is a 1 and the common ratio is q, the sum of the first n terms of the sequence a n is Sn. According to the general formula of the geometric sequence, we can represent the first n terms Sn using a 1 and q. By multiplying both sides of Sn by the common ratio q, we obtain equations 1 and 2. Subtracting equation 2 from equation 1, we get that Sn minus q times Sn equals a 1 minus a 1 multiplied by q to the nth power. This way, we eliminate these intermediate terms. Extracting the common factor, we get that 1 minus q times Sn equals a 1 multiplied by 1 minus q to the nth power. Now, let's think about this. If we want to solve for Sn, can we divide both sides of this equation by 1 minus q? Let's analyze specifically. When 1 minus q equals 0 and the common ratio equals 1, this sequence is a constant sequence, and its sum of the first n terms is n times a 1. When 1 minus q is not equal to 0, that is, the common ratio q is not equal to 1. We can divide both sides of this equation by 1 minus q to obtain sen equal to the first term a 1 multiplied by 1 minus q to the nth power divided by 1 minus q. Then, based on the general formula of the geometric sequence, we have a n equal to a 1 multiplied by q raised to the power of n minus 1. Therefore, we can manipulate this formula to obtain Sn equal to the first term a 1 minus the nth term a n multiplied by the common ratio q divided by 1 minus q. At this point, we have derived the formula for the sum of the first n terms of the geometric sequence. Let's consider when to use formula 1 and when to use formula 2 when the common ratio q is not equal to 1. Because the basic quantities involved in these two formulas are different, if the first term a 1 common ratio q and the number of terms n are given in the problem, we prefer to use the first formula. However, if the first term a 1, the nth term n, and the common ratio q are given in the problem, we choose the second formula. Let's summarize. We have obtained the sum of the first n terms of a geometric sequence. When the common ratio is 1, Sn equals n times a 1. When the common ratio is not 1, we have obtained two formulas for the sum of the first n terms of a geometric sequence. Secondly, in the process of summing using the formulas for arithmetic and geometric sequences, the mathematical ideas are consistent, and we need to explore their essence. The fundamental purpose of deriving the summation formula is to eliminate the intermediate terms. Combining the characteristics of the geometric sequence, we use the method of misplacing subtraction to obtain the formula for the sum of the first n terms of the geometric sequence. When using the formula for summation, we should first consider the two cases where q equals 1 and q does not equal 1. With the summation formula, we can solve problem 2. We know that problem 2 corresponds to a geometric sequence. Its first term is 1, the common ratio is 2, and there are 64 terms in total. Therefore, we substitute these three basic quantities into the summation formula and obtain S64 as the first term a1 multiplied by 1 minus the common ratio to the power of 64 divided by 1 minus the common ratio squared. After rearranging, we get 2 to the power of 64 minus 1. Actually, this number is already very large. It has exceeded 1.84 multiplied by 10 to the power of 19. If the mass of 1,000 wheat grains is approximately 40 grams, then the total mass of all these wheat grains would exceed 700 billion tons. This is approximately 981 times the world's wheat production from 2016 to 2017. Therefore, we know that the king cannot possibly fulfill his promise. Next, we will apply our knowledge to solve problems, seeking solutions under the following three conditions. Let's first look at the first question. If a1 equals 1/2 and q equals 1/2, find S8. Let's analyze the sum of the first 8 terms of the geometric sequence. To find the sum of the first n terms of a geometric sequence, we can use these two formulas, each involving different basic quantities. The first formula requires knowledge of the first term a1 and the common ratio q. The second formula requires knowledge of the first term a1, the eighth term a8, and the common ratio q. Based on the conditions provided in the problem, we choose the first formula to solve it. Since a1 equals 1/2 and q equals 1/2, S8 equals the first term 1/2 multiplied by 1 minus the common ratio raised to the power of 8, divided by 1 minus the common ratio 1/2. Through calculation, the result is 255 over 256. Let's move on to the second question. If the first term a1 is equal to 27 and the ninth term a9 is equal to a 243rd and the common ratio q is less than 0, find S8. In the previous problem-solving process, we have already known that we are seeking S8. It can be solved using a1, a8, and q, or using the first term a1 and the common ratio q. The given information in the problem includes the first term a1 and the ninth term a9. We can first calculate the common ratio q using these two terms, and then use the first term and the common ratio to determine the value of S8. Let's perform the calculation in detail. From a1 and a9, we can deduce that 27 multiplied by q to the power of 8 equals 1 to 143. Therefore, q to the power of 8 equals 1/3 to the power of 8. Since the problem states that the common ratio q is less than 0, the common ratio is equal to -1/3. We substitute the first term 27 and the common ratio -1/3 into the summation formula. The final result is calculated as 1,640 divided by 81. Let's ponder whether we can directly use this formula to calculate S8. Let's first look at this formula. There are three basic quantities involved, the first term a1, the eighth term a8, and the common ratio q. In this problem, the first term a1 is known, while the other two are unknown. However, we can first calculate the common ratio q using the ninth term a9 and the first term a1, and then complete the solution to this problem. Please complete it after class. Let's move on to the third question. If a1 equals 8, q equals 1/2, and Sn equals 31 divided by 2, find the number of terms n. We know that when q is not equal to 1, there are two formulas for the first n terms of a geometric sequence, each involving different basic quantities. Given that a1, q, and sen are known in the problem, we observe these two formulas and choose the first one to solve. Let's calculate it specifically. We substitute a1 equals to 8, q equals to 1/2, and Sn equals to 31 divided by 2 into the summation formula, which gives us the first term 8 multiplied by 1 minus the nth power of the common ratio, where n is the unknown variable divided by 1 minus the common ratio 1/2, which equals 31 divided by 2. At this point, only n needs to be solved in the equation. The calculated value of n is 5. Okay, let's think about it. For the relevant quantities in a geometric sequence, how many of the quantities such as the first term a1, the common ratio q, the number of terms n, the nth term n, and the sum of the first n terms sen are needed to determine the other quantities? We attempt to draw conclusions from the three exercises above. Firstly, in the first question, given the initial term a1, the common ratio q, and the number of terms n, we can calculate the nth term using these three quantities. We can also calculate the sum of the first n terms. For the second question, given the first term a1, the nth term, and the number of terms, we can first solve for the common ratio q using these three quantities, and then use the common ratio q and the first term to find the sum of the first n terms Sn. In the third question, given the common ratio q and Sn, we can use the concept of equations to first solve for the number of terms n. Then, using the first term a1 common ratio q and number of terms n, we can also find the nth term an. Therefore, we know that these 5 basic quantities related to geometric sequences should be found by knowing 3 and seeking 2. This reflects the application of the concept of equations in sequence problems. Let's summarize what we have learned in this class. In this class, we derived the formula for the sum of the first n terms of a geometric sequence. When q equals 1, Sn equals n times a1. When q is not equal to 1, we obtain two forms of the formula for the sum of the first n terms. Secondly, we employed the method of misplaced subtraction to derive the formula for the sum of the first n terms of a geometric sequence. The third, after obtaining the formula for the sum of the first n terms of a geometric sequence, if any three of the 5 quantities, namely the first term a1, the common ratio q, the number of terms n, the nth term n, and the sum of the first n terms n are known, the remaining 2 can be calculated. This demonstrates the application of the equation concept in sequence problems. Equations play an important role in algebra. That's it for this class. See you all later.